Every night, we look up and see a constant companion, a silver sentinel that has watched over Earth for over 4 billion years. It pulls at our oceans, stabilizes the very axis on which our planet spins, and has cast its pale glow over every civilization, every war, every love story, and every funeral this world has ever known. Ancient sailors steered by it. Ancient farmers planted by it. Ancient priests built temples precisely aligned to it. The moon is not just a rock in the sky, it is woven into the fabric of what it means to live on this planet. But the moon is keeping a secret. It's leaving us. Right now, as you read these words, the moon is spiraling outward into the cold dark of space. It's not a sudden leap, it's a slow, agonizing crawl, about 3.8 centimeters per year. That's roughly the same speed at which your fingernails grow. Take a moment and really sit with that. The distance between Earth and the moon is growing at this very second at the exact same pace as something you trim off your fingertips without a second thought. In the grand scale of the cosmos, 3.8 centimeters is nothing. But multiply nothing by millions of years and you get something extraordinary. Those centimeters compound into kilometers, into thousands of kilometers, into a distance that will fundamentally and irrevocably alter the world as we know it. Today, we are diving deep into the celestial mechanics of the Great Lunar Retreat. Why is it happening? What are the cascading consequences as the moon drifts further into the void? What happens to our tides, our seasons, our eclipses, and the very length of our days? And what does a future Earth look like without its oldest partner? To understand why the moon is running away, we first have to understand the invisible physics at play between our two worlds. This is the story of tidal friction, and it is stranger and more elegant than most people realize. Most of us learn in school that the moon causes the tides. Its gravitational pull stretches Earth's oceans into a slight bulge on the side facing it. What we are rarely taught is what happens next, and that's where things get genuinely mind-bending. Earth is not a static object. It's spinning, and it's spinning much, much faster than the moon orbits around it. Earth completes one full rotation in 24 hours. The moon takes about 27 days to complete a single orbit. Because of this speed difference, Earth's rotation drags that tidal bulge of water slightly ahead of the moon's orbital position. Think of it like a water balloon being spun faster than the hand holding it. The water sloshes forward, leading the pull. Now here is where the physics gets trippy. That bulge of water has mass and therefore gravity of its own. Because it sets slightly ahead of the moon in its orbit, it exerts a tiny but real gravitational tug on the moon, pulling it forward. And in orbital mechanics, adding forward energy to an orbiting body causes it to rise into a higher, more distant orbit. Earth is quite unintentionally kicking the moon further away, one small tug at a time, year after year, for billions of years. But there is always a price to pay. Newton's third law is non-negotiable. For every action, there is an equal and opposite reaction. As Earth's displaced gravity pushes the moon outward, the moon's gravity exerts a braking force on Earth's rotation. It acts like a giant, invisible hand pressed against a spinning wheel. The result? Earth is slowly winding down. Hundreds of millions of years ago, a day on Earth was not 24 hours. It was closer to 18 hours. Our ancient planet spun so fast that a year contained far more days than it does today. We are literally spending Earth's rotational energy like currency, paying it out into space to fund the moon's slow departure. You might reasonably ask, how can scientists possibly measure a change of a few centimeters across 384,000 kilometers of empty space? The answer is surprisingly poetic, and it comes down to mirrors. Mirrors left behind by human beings who walked on another world. During the Apollo 11, 14, and 15 missions, astronauts deployed small arrays of corner cube laser reflectors on the lunar surface. These are precisely engineered prisms that reflect light back in exactly the same direction it came from, regardless of the angle of arrival. For over 50 years, observatories across the Earth have been firing high-powered laser pulses at these reflectors. By measuring the round-trip travel time of the laser light to the nanosecond, divided by the speed of light, scientists can calculate the distance to the Moon with millimeter-level precision, millimeters, across almost 400,000 kilometers of space. The data is unambiguous. The Moon is receding at 3.8 centimeters per year. But we don't have to rely solely on modern lasers for confirmation. The Earth itself has been keeping records far longer than we have. Geologists study formations called tidal rhythmites, ancient layers of sediment deposited in prehistoric estuaries and tidal flats. As the tides rolled in and out over millions of years, they left thin, regular bands in the mud, like pages in a book written by the ocean. By counting those layers, each one representing a tidal cycle, scientists can reconstruct how many tidal cycles occurred per year in the deep past. That number tells us how close the Moon was, and the answer is extraordinary. Around 1.5 billion years ago, the Moon was significantly closer to Earth, perhaps 340,000 kilometers away instead of today's 384,000. A month was shorter, a day was shorter, and if you had looked up at the night sky from that primordial world, you would have seen a moon noticeably larger and brighter than the one we know, a giant silver orb hanging over an ocean world ruled by bacteria and microbial mats before anything with eyes had evolved to appreciate the view. So what happens as that distance keeps growing? The effects unfold across multiple timescales, and they are more profound than most people ever consider. The first casualty is one of the most beautiful coincidences in the known universe. The Moon is almost exactly 400 times smaller than the Sun. The Sun is almost exactly 400 times further from Earth than the Moon. This numerical alignment, which has no deeper cosmic purpose, no design, no intention, is what makes total solar eclipses possible. When the Moon passes in front of the Sun, it covers it almost perfectly, allowing us to see the Sun's delicate, wispy corona and creating that breathtaking diamond ring effect as the last sliver of sunlight blazes around the lunar edge. It is one of the most awe-inspiring sights a human being can witness. Entire expeditions have crossed the globe throughout history just to stand in the path of the Moon's shadow for a few minutes. In approximately 600 million years, it will be gone forever. The Moon will have drifted far enough away that it will appear too small in our sky to fully cover the Sun. Future inhabitants of Earth, whoever or whatever they may be, will experience annular eclipses only, a ring of sunlight forever visible around the Moon's silhouette. The era of totality will be over. The corona will be hidden again. That particular cosmic coincidence will have run its course. But the loss of eclipses, while poetically devastating, is not the most consequential effect of the Moon's retreat. That title belongs to something far more fundamental: axial stability. Earth's axis is currently tilted at about 23.5 degrees relative to its orbit around the Sun. This tilt is the reason we have seasons. It is why summers are warm and winters cold, why days are longer in summer and shorter in winter, why the agricultural rhythms that allowed civilization to develop are possible at all. The Moon acts as a gravitational anchor, keeping this tilt stable over millions of years. Without it, or with a Moon too distant to exert meaningful influence, computer models suggest Earth's axial tilt could become chaotic, swinging wildly between 0 degrees and as much as 85 degrees over millions of years. The implications of a tilted-over Earth are catastrophic. At 85 degrees, a planet essentially lies on its side. The poles point almost directly at the sun during summer, receiving months of continuous direct sunlight, while the opposite hemisphere plunges into months of unrelenting darkness. Seasons would not be the gentle rhythm we know. They would be violent, extreme oscillations between scorching heat and absolute cold. The stable climactic conditions that allowed complex life to evolve and flourish over hundreds of millions of years would be gone. Earth would become a hostile, chaotic world. Meanwhile, Earth's rotation continues to bleed away. As the moon retreats and our spin decelerates, days grow longer, not at a pace any of us will ever notice in a lifetime, but inexorably, across geological time. We are currently gaining about 1.4 milliseconds per century. It sounds trivial, but run that forward through millions of years and the days stretch dramatically. This process is building toward a theoretical endpoint called mutual tidal locking. In the far, far future, if allowed to proceed uninterrupted, Earth's day would eventually grow long enough to exactly match the moon's orbital period. At that point, Earth would no longer rotate relative to the moon at all. One hemisphere of Earth would permanently face the moon. The other hemisphere would never see it. People on the moon-facing side would watch it hang fixed in the sky like a painted ornament. People on the opposite side would know the moon only as a legend, a myth from books, something you had to make a long journey to ever see with your own eyes. It is a profound, almost philosophical image, a world split between those who see the moon and those who never will. But there is a critical catch. This process requires billions upon billions of years to complete, and the universe has already made other plans for our solar system. In approximately 5 billion years, the sun will exhaust its hydrogen fuel. As the nuclear fusion in its core shifts and sputters, the sun will swell outward into what astronomers call a red giant star. Its outer layers will expand enormously, potentially engulfing Mercury and Venus and scorching Earth beyond any recognition of the world we know. The inner solar system will be a different, fire-soaked place. For the moon, the red giant phase introduces a new and ironic force. The sun's expanding outer atmosphere will create a diffuse gas drag on the moon's orbit. Instead of continuing to spiral outward, the moon will begin to lose orbital energy and spiral slowly inward. The Great Lunar Retreat will reverse. The runaway will come home, not by choice, but by physics. And as the moon falls back toward Earth, it will approach a boundary that has its own name in celestial mechanics, the Roche limit. Named after the French astronomer Édouard Roche, who calculated it in 1848, the Roche limit is the distance at which a celestial body held together primarily by its own gravity begins to be overwhelmed by the tidal forces of a nearby larger body. For the Earth-Moon system, the Roche limit lies roughly 9,500 kilometers above Earth's surface. If the moon were to cross that threshold, the differential gravitational pull across its diameter would exceed the internal forces holding it together. The moon would not crash into Earth, it would not explode, it would come apart, slowly and then all at once, fragmenting into billions of pieces, ranging from mountain-sized boulders to fine gravel to dust. The debris would spread around Earth in a ring, encircling our planet in a shimmering, glittering band of pulverized moon. For a brief and spectacular window in geological time, Earth would have rings. Not quite like Saturn's broad, iconic bands, ours might be denser, rockier, more chaotic, but rings nonetheless. The remains of our companion, stretched into a halo, orbiting the world it once governed. It would be one of the most astonishing sights in the history of the solar system, a world draped in the wreckage of its oldest relationship. Gradually, over millions of years, that ring material would disperse. Some would drift away into space. Some would rain down onto Earth's surface as a prolonged meteor bombardment. And eventually, the sky would clear, and the moon would simply be gone. We live in a golden age of the Earth-Moon relationship, and almost no one knows it. We are here at the precise moment in cosmic history when the moon is close enough to be magnificent, when its gravity is strong enough to circulate nutrients through our oceans and sustain the marine ecosystems at the base of our food chain, when it holds our axial tilt stable enough to produce predictable seasons that agriculture and civilization depend on, when it is the perfect size to produce total solar eclipses, and when it is close enough that human beings built rockets and actually went there. That window is not forever. The moon's slow departure is a reminder that nothing in the universe is truly static. We speak of the stars as timeless, of the sky as unchanging, of the moon as a permanent fixture, but the universe is always in motion, always evolving, always heading somewhere. Stars are born and die, galaxies collide, orbits drift. Even the most solid-seeming anchors in the sky have their own stories, their own journeys, their own endings. Every year, the moon has a tiny 3.8 centimeter goodbye. It will not be gone in our lifetime, or in the lifetime of any human civilization we can reasonably imagine. We have hundreds of millions of years of tides, eclipses, and moonlit nights still ahead of us, but the process is real, it is measured, and it is relentless. So the next time you step outside on a clear night and find the moon hanging there full and bright and close, pause for just a moment. Look at it without taking it for granted. Understand that the ocean tides moving beneath it are the very mechanism pushing it away. Understand that the length of your 24-hour day is slowly growing because of it. Understand that total solar eclipses exist because of an alignment so precise and so temporary that future beings may never know what one looked like. We are in the middle of a slow, magnificent breakup, one measured in centimeters and billions of years. And the view right now, it's extraordinary. Enjoy it while it lasts.